Okay, this is the 3 notes for Calculus 1. This is a big section for students, mostly because this is where you learn how to find the shortcut formulas or compute the shortcut formulas for differentiation. If you recall from our first section in this chapter, you learned that the derivative of the function is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, this meant that we had to go through that process of finding this formula for, and it took forever, if you recall. It took, sometimes problems took as many as 2 to 3 minutes, so that will not be the case anymore. What this section does is it streamlines the process by using rules of differentiation right up front here. So, before we get started, I just want to be clear on a couple things. So, let's say that I had some function, let's say f of x is equal to, let's just say 2x plus 1. Let's just actually do 2x, okay? So let's say that's my function. So terminology-wise, if I want to find the derivative of x, then you normally would just use this formula on this, 2x right here. But before that, if I want a terminology speak, if I say, hey, find the derivative, that's going to not look good. Find the derivative. Another way to write that is, say, d dx of 2x. Okay, so basically all this is saying is take the derivative of the function f of x equals 2x. So this is important only for what we're going to do here. Basically, if you have an original function, f of x is 2x, and I want to find the derivative, that's equivalent to finding d dx of 2x. It all lead to the same place. But this d dx basically says find the derivative of this with respect to x. So if you look at our theorem here, it says if c is a real number, well, by real number we say, well, that's a constant because there's no variable involved. It states that d dx, so the derivative of respect to x, which is this terminology, of a constant c is always going to be equal to 0. So what does this mean exactly? If we use this terminology over here to help us break this down, we're basically dealing with a function f of x is equal to c. So just think of c as any number, 5, 8, -7, pi, whatever it is. It's just a number. There's no variable involved with it. So what's saying is if we take the derivative of this function, we are always going to get 0. Okay, so just as an example, I know this is going to be very simple, but if we go down to right here at number 1, that if we go by this logic, then the derivative of the function 8, according to this, is always going to be equal to 0. Okay, that was a really easy problem, right? But let's get a little bit deeper into it. So if I have a function f of x equals c, and for example, in this problem, this would be f of x equals 8. Well, what is f of x the same as? It's the same as y, right? So y equals 8, what is that? So what's that the graph of, y equals 8? Well, hopefully, when you think about it, if I have a graph and I go up 5, 6, 7, 8, then the graph of that line is actually horizontal. Okay? So recall that the derivative, so this right here, the derivative is the slope of the tangent line. Okay, so if I go to this line right here and I draw a tangent line anywhere at any point, I'm going to get also a horizontal line. And what do we know about the slopes of any horizontal line? It is, of course, 0. Which means all this formula states is if you take the derivative of a constant, the constant being essentially a horizontal line on the plane, coordinate plane, then any slope of the tangent of that line will be 0. So anytime you run into a problem where you have the derivative of a sole constant without a variable, the derivative is always going to be 0. Okay, so let's get into the real big one, the big theorem here. So this is essentially the power rule. And so what does the power rule state? It says if you take the derivative of any function, which is x to some power, so x to some power, then the derivative of said function is always going to be this quantity, n times x to the n minus 1. So, what does that appear is happening? It appears that the exponent in the original problem appears to be going to the front as a multiple, and then you're doing x2, and then the power that you end up is 1 less than the power you had before. Okay, so it seems a little crazy, and literally by the end of the lesson you should be doing this like a rocket ship because it's a really simple method. The best way to really hammer this out is to look at an example. So look at 2. So let's say we find the derivative of x squared. So of course in this problem 2 is n. So if we want to figure this out, what would we do? Well, according to this, here's your formula. Where does n go? It ends up going to the front of the problem as a multiple, 2 times. We keep the variable, but then, according to this, we have to take our 2 and subtract 1 in our exponent. So what do we get when we do that? We get 2x to the 1, which is just 2x. So guess what? This is the derivative of x squared. So the process itself, obviously right now you're just working it out, but this is the type of formula where students are doing this in a split second along the line here. But that's essentially what the process is about. It's about being able to come up with that as a side note. So just to be clear, let's say we did, let's say x to the 12th, right? So I'm just going to do, let's say 2b over here. So if I did the derivative of x to the, let's do 11. So x to the 11th, so what would that be? 11 would come to the front, x would stay, and then you would have to do 11 minus 1. So what do you get? You get 11x to the 10th. So that would be the derivative of this function. So all you do is move this number to the front, over here, and then subtract 1. That's it. Super fast. That is the power rule in a nutshell. Okay, so last theorem up top here with these guys. So what if you have a function that is differentiable at x? So let's say you have an f of x function. So essentially there's a variable involved in the function, but then you have a constant multiplied in front of it. So to be clear, this is not a constant like up here where there's no function involved and it's just a number like 8. This instead is a number that is multiplied, a multiple, in front of, or around, in this case, a function. Okay, so what happens? It turns out that you do nothing with the constant and multiply it by the derivative of the function itself. Okay, so this is where it might get confusing with all these variables, but the best way to really accomplish this is to do an example. So if we go down to, let's say, number 3, look at what we have. We have a constant c multiplied by a function f of x. So we have a constant, which was 8, and we have a function, which is x squared, but now we have them both in the same problem being multiplied. So what do we do with that? So according to our process, in this theorem right here, this is the same as just taking 10 times the derivative of x to the 5th. Now it doesn't fit necessarily the formula the way you see it here, but this is the best way to think about it, is that the 10 basically just comes along for the ride. That's what I'm going to say that a lot in my videos. Basically, it's there and it's watching. It's not doing anything, nothing's happening to it. Comes along for the ride, but we have to take the derivative of the function itself. So what does that look like? Well, we keep the 10. What is the derivative of x to the 5th? Well, again, we did x squared and we did x to the 11th, so we should be able to do x to the 5th. So what happens? Returning to this here, what do? We move 5 to the front, we keep the x, and we subtract 1 from the exponent. So right now we have 10 times 5x to the 4th, which means we can multiply that and get 50 x to the 4th as our derivative of 10x to the 5th. Okay, so last problem here. The blue. So let's say we find the derivative of 5x. Now 5x is the same process, so if you look here, let's get rid of the noise here. So if you look at this formula, it's the same thing. What do we have? We have a constant in front of a function. The function is just very simple. It's x itself. So how do we accomplish that? Well, what do? The 5 comes along for the ride. The derivative of it is not 0. It's not like this. It's not a sole constant. It's a constant in front of a function. The 5 comes along for the ride, and you have to find the derivative of x. So what does that look like? Well, let's follow the process. So obviously x itself does not have an exponent on it to be seen, but literally it is a 1 that's just there and it's hidden, so to speak. So what happens? The 1 comes to the front. We take the x and then we go to the 1 minus 1 power. Okay, so what does that look like? Well, this is going to be 5 times 1, which is 5, x to the 0. Well, what do you guys know about anything to the 0 power? It is equal to 1. So this whole thing is 5 times 1, which is 5. So the derivative of 5x turns out to be 5. Now, a little bit of a shortcut for you. Anytime you have a constant with just the x, the derivative is just going to be the constant. So if I said, what's the derivative of 100x? What would it be? It would be 100. If I said, what's the derivative of, all right, let's give you guys some stress, of pi x. What's the derivative of pi x? It's pi. It's still a constant that's in front. So in this scenario, these guys, it always happens that way, so you don't have to do this calculation out. You can memorize that that is always the case. Okay, so before I move on, what I want to do is I want to sort of look at this entire concept right here, right? This whole concept. So in every problem, we found a derivative for each one of these functions. So what I don't want you to do is lose track of the overall theme of this entire process. So basically you start with a function. So for the first problem, we had the function f of x equals 8. Okay, this is a graph of a horizontal line. For this function, we have f of x equals 10x to the 5th. This is a polynomial graph, a funky one, but a polynomial graph. Here we had f of x is equal to x squared, which is a parabola. Here we had f of x equals 5x, which is a line. So what do the answers, the derivatives, actually mean? The derivatives are, again, the slope of the tangent line at any point. So I want to be very clear here, since most students understand what x squared is. So they know that it's the graph of the very simple upwards facing parabola, right? Or quadratic function is more like what you guys are used to hearing. But it's a parabola. So that means that if I pick any point on my parabola, any point, so let's say here, let's say x equals -1, okay? If I draw a tangent line at that point and I want to know its slope, then all I have to do is plug -1 into my derivative, and I'm going to get the slope of that line. So for example, here, the slope would be -1 times 2 is -2. So the slope of this line is -2. Okay, that is what we're finding. So even though I'm giving you all of these wonderful theorems and rules, do not lose track of the little stars here, these stars. Do not lose track of that these functions tell you what the slope of that line will always be, the tangent line. That is what the point of all of this, of why we're doing it. Okay, so why don't we get into a little bit more challenging material to make sure that you are completely algebraically prepared for what you're going to embark on here. That's the best way to put it. So sometimes you're going to have to find the derivatives of functions that are not all so easy. You'll have fancy formulas to help you out along the way, but sometimes it's not about being fancy, it's about just knowing your algebra. For example, look at number 5. It says, what is the derivative of 1 over x? Okay, you will have something called a quotient rule later in our chapter, actually the next section. But for now, this does not need that. It is a quotient, but it does not need that. Why? Because whenever we have a constant in the numerator, we can always move the variable in the denominator to the numerator. So you might go, whoa, like, how do you do that exactly? Well, just remember that this is 1 over x to the 1. You learned about negative exponents in algebra. Well, how did you learn about them? Well, basically, if you had x to the negative 3, you learned that negative exponents move a quantity from numerator to denominator and vice versa. So this would be the same as 1 over x cubed. But that also means that we can go in the opposite direction. So if I had 1 over x to the 5th, that is going to be the same as x to the negative 5. So I can move it to the numerator and make the exponent negative, just like this guy here. I can move to the denominator and make the exponent positive. So what do we do with this? Well, this is positive in the denominator, so let's move it to the numerator and make it negative. So that means that this is the same as the derivative of x to the negative 1. Okay, so why was that so important? Because look at our formula up here. Let's get rid of the stuff here. Look at our formula. Isn't that the same, but now n is negative 1. So look, so this here is n, which means what do we do when we find the derivative of the function? The n goes to the front, so negative 1 goes to the front. We copy the variable, the base of the exponent, and then we do negative 1, which was there already, minus 1. So remember, again, n goes to the front, and then we subtract n1 from the exponent there. So what do we get? We get negative 1x to the negative 2. Okay, but if we start with a fraction, we always want to end with a fraction, and normally we don't leave negative exponents as is. So what is that equal to? Well, the negative 1 stays put, and then we move x to the negative 2 to the denominator and make the exponent positive and get negative 1 over x squared. So the derivative of 1 over x is negative 1 over x squared. So I found in previous calculus classes, I've taught this class a trillion times, what I found is that after me showing that to students, 2/3 of the class is like, I got it. But there's always that 1/3 of the class, maybe a fourth, that look at this and go, oh boy, time to recall algebra. So just, if that's you, make sure you do that. Make sure that you get lots of practice. You do not want to screw up calculus because you don't remember your algebra. It's just a shame that that would happen. So make sure that you study that stuff when you're going along the way. One thing I want to point out that I didn't mention so far with this stuff is just remember, just like when we applied the limit of a function, the limit disappeared. It's the same thing with this ddx stuff right here. So the ddx disappears as soon as we apply it to the actual function and then get the derivative. So like here we have the derivative of x to the 5th, but then as soon as we take the derivative, ddx disappears. Same thing here, we have ddx applied to the function x to the negative 1. As soon as we apply it, the ddx disappears. I just wanted to point that out. Alright, so next part here. So here's another function that doesn't look fun. So currently we have the derivative of the square root of x that we're looking for. So we don't have any formulas for roots yet, or really ever, to be honest with you. So that means that we have something else going on here. So again, just like in the same theme as what I did for number 5, for number 6, again, what did you learn in algebra about exponents when it comes to radicals? Let's do a review. So first things first, the square root of x is the same as x to the 1/2. Okay, so this is going to be the derivative of x to the 1/2. Now again, 2/3 of the class, usually 3/4 of the class is like, oh, I remember that. And then the other part is like, uh-oh. So again, you got to know this stuff. So I'm going to go deeper though. So what if I said the cube root of x to the squared, x squared? What is that equal to? Well, that's equal to x to the 2/3. So whatever's in the root is always in the denominator of the fraction, the fractional exponent, and whatever the power is on the actual variable is going to be in the numerator of the fractional exponent. So, and whenever you see a radical, you immediately change it to this before finding a derivative. So, again, what is this the same as? This is the same as our formula right here, but this time n is a nasty fraction, right? So how do we handle it? Same time we always do. So drop the derivative, because we're finding it. 1/2 goes to the front. Then we have the base variable, and then we subtract 1 from the exponent itself. By doing that, we get 1/2 x to the negative 1/2. Okay, so things are getting nasty here. So what does that look like? Well, just remember that this is 1/2, and this is x to the negative 1/2 over 1, right? So what happens? So right now we have x to the negative 1/2 in the numerator. We can't leave it that way because there's a negative exponent. So we move it to the denominator, leaving just 1 times 1 in the numerator and getting x to the positive 1/2 in the denominator times the original 2. Again, normally we don't leave fractional exponents, especially if we started with a radical. So we need to turn it back. So we get 1 over 2. Well, what's x to the 1/2 the same as? It's the same as root x. So we get root x. So this is the derivative of our function root x, 1 over 2 root x. Now, what I will say is you will probably be doing this calculation with roots for a while. And if you get like the cube root of x or the 4th root of x or something like that, absolutely use this formula. But the square root of x comes up a lot. So even though it's not like a formal derivative rule that you memorize, I would do that anyway. I would memorize that the derivative of root x is always 1 over 2 root x, only because of the frequency in which you're asked to find that derivative. You might look at this now and be like, not a big deal, but you have no idea what we're about to embark on when it comes to the complexity of the derivatives we'll do, and knowing this formula will save a tremendous amount of time on what we do later. All right, let's take a peek at number 7. So I have a star next to this problem because it's a little odd, but I provide it to students. It does come up, I think, in homeworks, labs and such. But I do provide it to students mostly because I want to prove the concept of you always follow the derivative rules to the letter of the law, no matter how bizarre they look. So we basically have this function here, 10x to the w plus 4. What's new? This weird w. So the key is, once again, we are taking the derivative with respect to x, so we don't really care that much about the w. We have to apply it with respect to the variable x. Now, if you look at this, this actually fits our derivative rule right here. So we have a constant in the front, our c, and we have a function f of x next to it. So just like we've done before, that means the 10 moves to the front, comes along for the ride, basically, and we have to take the derivative of x to the w plus 4. Okay, so x to the w plus 4 is basically a perfect example of the power rule. It's x to the n. But now, instead of n being a number, n is an expression. Okay, so what do? Well, we don't do anything different than we normally do. Keep the 10. What is the n value that needs to go to the front in the derivative function? It is w plus 4. So that goes to the front, right, of our derivative function. We keep our variable x, and then we have to do what with our exponent? Well, again, what do we have to do with our exponent right here? We have to subtract 1. Whoa, I went too far. So we have to subtract 1. I know it's looking crazy, right? But doesn't matter. We can keep this guy, right, as is. And then w plus 4 minus 1 is w plus 3. Even though we can distribute this if we wanted to, we don't need to. So therefore, this is going to be the derivative of this function. We don't know what w is, so there's nothing we can do with it. we can't find the derivative of it because we're trying to find the derivative with respect to x, not w. So w is just hanging along like it's just any old number, specifically a positive integer. So this is a little weird, but the key is, note, I didn't abandon the derivative rule. Even if it looks heinous, you still don't abandon those rules. You still stick with it and follow them as you normally would. Okay, let's move on to our next theorem. So what we basically, if you looked at all of the values up here, they were all one-term quantities that we dealt with. So just 8, just x squared, just 5x. So what if, let's say, we ended up with multiple term quantities? So like here, there's, 4 terms going on here. So how do we deal with that? Well, we have what's called the sum rule. I also call it, it can also be differences are also applied to this sum rule. So technically, it's kind of the sum difference rule. So basically what it states is if you have the sum of 2 functions and you want to find the derivative of that, it's the same as finding the derivative of each one of those functions and then just bringing down the sign. So essentially you can distribute the derivative to each quantity that's in there. Why is this useful? This is most useful for polynomials or any functions that have multiple terms in them. So if you're looking at, let's say, number 8, I have 4 terms. This theorem is basically stating that this is equivalent to the derivative of 2x cubed, bring down the sign, minus the derivative of 4x squared, bring down the sign, plus the derivative of 10x, plus bring down the sign, derivative of 15. So I'm not going to require that you write it this way every time. Most students are going to get the hang of this very quickly, and they're just going to say, okay, what's the derivative of 2x cubed? What's the derivative of 4x squared? 10x, 15x. And they're just going to write it out as they go, and that's fine. But we're going to do this out once at least just to make sure that you're clear on what you're supposed to do. Okay, so by now, hopefully you're cruising. We've done 7 problems when it comes to using these derivative rules, so hopefully we can start doing a little bit of shortcut work. So what does that mean? So 3 is n, right? And so if we're doing x cubed, first of all, the 2 right there, 2, is a constant. So technically it goes along for the ride, but what if we made this a little bit quicker? So for example, in, let's go to here. So in this problem right here, what did we do? We basically took the 10, right, and we moved it to the front and then isolated the exponent. But what if we hadn't done that? What if we just said, okay, take the 5, move it to the front, multiply by the 10 and get 50, and then subtract 1 from the exponent and get x to the 4th? Man, that would be super easy, folks. So let's do that here. So what are we going to do? We're going to take our 3, which is here. We're going to turn it to the front, multiply by 2, and get 6. Subtract 1 from the exponent and get 6x squared. Bring down the minus sign. Same thing here. The 2, move it to the front, multiply by the 4, and get 8. Subtract 1 from the exponent and get x to the 1, which is x. Go to the next one. What about 10x? Well, this should ring a bell. We already did it once, though. If you go back to this problem, what's the derivative of any constant multiple times just x? Well, what did we keep on getting? We kept on getting the constant multiple. So the derivative of 10x is just 10. And then finally, actually, let me spread this out for you just to make sure that this is all good. So this is 6x squared. This is 2 to the front, 8x. This is 10. And what is the derivative of 15? So hopefully you're screaming at me the result. The derivative of any constant is a 0. Okay, so what is that equal to? Let's go back to green here. That is equal to 6x squared minus 8x plus 10. Okay, so that is essentially the derivative of our third degree polynomial. The derivative is a 2-degree polynomial. So again, don't abandon the logic here. So if I have some cubic graph, who knows what it looks like? Let's just make it up. Let's say that's a cubic polynomial. If I want to know the slope of the tangent line at, let's say this is at x is equal to 5, right? Then if I want to know the slope of this line, I have to plug 5 into this function, and it'll give me the slope of the line. Okay, so we're going to get to that in a second. We're going to do full problems like that, but I don't want you to, again, we learned a new theorem. Don't lose track of what we're actually trying to find. Okay, let's do a doozy. Call this a doozy. Number 9. So the derivative of 3 over x squared plus 6 times the cube root of x squared. Okay, so yes, insanity, but hopefully you already see that what I'm doing is I'm combining the sum rule with these two problems. Okay, we have a quotient here and we have a radical. So we're combining the same concept. So the key is before we get started, we know that this is the same as the derivative of each quantity, 3 over x squared. Bring down the plus sign times the derivative of 6 cube root of x squared. Okay, that's the first step. What did we apply? We applied the sum rule. But hopefully you understand by the problem we did before that we cannot apply any of the rules that we know so far with either of these functions. Either one, these two. Can't apply in any without altering them. So what do? We have to change them into basically powers. So x to the second is in the denominator. We want to move it to the numerator and make it negative, so x to the negative second is our value. Now we have a constant times x to a power. We are good there. Derivative of x. Now we have to find the derivative of this. So what do we have? We have a 6 constant, and then we have x to what power? So what do we say? Any radical is a fractional exponent, where the actual root is in the denominator and the power is in the numerator. So this is x to the 2/3. So just to be clear, we didn't do anything with derivatives yet. All we did was use algebra to convert these to quantities that we can find the actual derivative of using the formulas that we know. So let's actually do this step first down here. So what do we need to do? We need to find the derivative. So again, what do we do with the exponent? We take the exponent, move it to the front, multiply by 3, and get negative 6. Keep the x as is, and then we need to subtract 1 from the exponent, but be very careful with negatives. Negative 2 minus 1 is negative 3. I'm sure most of you will realize that some students will make a mistake and make that negative 1. Just be careful on the negative side of things. Bring down the plus. All right, so 2/3 the fraction. We're multiplying 2/3 times 6. So 2/3 of 6. So that's going to be 4. So 4 is in the front. Then we need to subtract 2/3 minus 1. So x to the 2/3 minus 1. Well, what's 2/3 minus 1? Well, you're going to have a calculator, but what's the easier way to know that? 1 is the same as 3 over 3. So 2 over 3 minus 3 over 3 is negative 1/3. Okay, x to the negative 1/3. So we basically have the quantities by taking the derivative. So note, that wasn't that easy, I guess, mathematically compared to the other things we did, but it's still very doable in terms of the quantities. So now, let's go in this direction. So now we just have to make this clearer. So negative exponents go back to the numerator and become positive. And then what happened along the way here is our positive fractional exponent in our derivative became negative, so that also has to move to the denominator and become positive. So this is the answer to our problem. If you want to get very technical, actually, let me just erase this. If you want to get very technical, you can say this. You can say negative 6 over x cubed plus 4 over the cube root of x. This is probably the better way to write it because we started with a radical, but you get the idea of what this is. So this might look like an absolute insane looking formula. You have seen nothing yet. You're going to see things that are going to blow your mind with in terms of derivatives. So this is just a very straightforward basic one at the beginning of what we're doing. So realize that that is the derivative of our function. Okay, so moving on, sort of a jump into a new topic here in the same chapter. So far, you've dealt with mostly polynomials, which is what you dealt with here, right? Polynomials. And anything that can be converted into a power. So a power is anything x to a constant value. So, just to be clear, I'm going to go down here. So if I had f of x equals x to the b, this is called a power function because it's x to a number. So for example, x squared. Okay, we'll do f of x equals x squared. But what if we reversed the b and the x and got f of x equals b to the x? This is called an exponential function, which you learned about in pre-calculus. So what's an example of that? It would be f of x equals 2 to the x. So clearly, what happened here, we are reversing the base and the exponent. Okay, the derivative for finding an exponential function is nothing like the derivative of finding a power function. Along the way, you will be given a ton of formulas based on the different types of functions that we have in calculus, pre-calculus, mathematics that will show you how to compute derivatives, essentially. So what's our first one? The derivative of b to the x. So what are the requirements? The base of the function can't be 1, and it has to be strictly positive. So no negative bases, and we can't have a base to be 1 because 1 to any power is just 1. So we're stuck with sort of that. So the derivative of b to the x is always going to be equal to this formula you must memorize. B to the x natural log of b. So for a lot of you, this is the first time you saw natural log since the beginning of pre-calc or pre-calc 1, depending on if you took it, what school you took it at. So we're basically, logs are now in full effect of what we're doing. So we're not going to have to learn a lot about logs. I'll review along the way, but generally that is what you'll have to know as a formula. So what does that mean? So the derivative of an exponential function is repeat the exact exponential function to start, then multiply by the natural log of the base of that exponent. Okay? So that is the formula we're going to use in this standpoint for an exponential function. Now again, what if there's a unique case in which the base is actually our very famous number e, our exponential e constant? If we have the derivative of e to the x, believe it or not, it is equal to itself, e to the x. So why is that? So what I want you to do is I want you to look at the formula d to the dx of e to the x, but what we're going to do is we're going to apply this formula to it, because technically this is e to the x is a b to the x. B is any number that fits these criteria. So we could plug e in there. So what if we did that? What if we followed this formula instead? We would repeat whatever we have, and then we would do the natural log of the base. Well, what's the base? It's e. Well, if you recall from pre-calc, the natural log of e is equal to 1. So what is e to the x times 1? It's equal to e to the x. So look what happened here in these two values. So I muffed that up. Isn't that exactly this? Right? Derivative of e to the x equals e to the x. So what does that all mean? So let me get rid of all this. I'm going crazy with our math here. So if you look at this guy, basically there are two formulas for exponentials. You always want to use this formula for e to the x because, duh, it's itself. It's the easiest formula that there is, basically. But this, which doesn't come up as often, you need to memorize that formula and know it. I will say that students often don't and then regret it on the exam. Okay, so obviously best way to understand this is to talk about a derivative example with this in state. So what do we have? We have the derivative of 5 to the x plus 3e to the x. Okay, well remember this is the derivative of a sum. Whether it's a difference or a sum, it doesn't matter, but generally what do? We find the derivative of each piece and bring down whatever sign is there as we go. Alright, so what comes next? So let me do this in a different color. What is the derivative of 5 dx? Well, 5 is not e, so we say it's generically just b. So what happens if we employ this formula? Well, according to this, the derivative is we bring the 5x as is, copy it down, then we multiply by the natural log of whatever the base is, 5. So the derivative of our first part is 5 to the x natural log of 5. We bring down the sign. What's the derivative of 3e to the x? Well, again, this is c, and this is our function. So c in this problem is 3. It comes along for the ride. So 3. What is the derivative of e to the x? Well, the derivative of e to the x is just e to the x. So believe it or not, the derivative of 3e to the x is 3e to the x. And this is our derivative of our function. Just a side note here, where do you want to be very careful? Well, students will look at e to the x or 5 to the x, and they'll go, ooh, it's a power. So they'll take the x and move it to the front and get like x 5 and subtract 1. I will convulse on the floor, if you get where I'm going with this, and it will be completely wrong. So remember, even at the beginning of this, you need to identify these as exponential and use the proper theorems when you're doing so. Alright, so next sort of concept within itself here. So we can also find higher order derivatives. So if you think about it, when we find, let's say, let's go to our polynomial. So when you find the derivative of this, you also get another function. So there should be no reason why we can't find another derivative of this. So you might look at that and go, Jesus, why would we want to find a second derivative? Well, the second derivative of a function also has meaning in our next chapter. We could keep on going and find the third and the fourth derivatives, which don't really have meaning for what we're going to be doing, but it's good for practice and understanding what you need to do. One thing that you want to take note of is terminology-wise. So while the first derivative is f prime of x, the second derivative is f double prime, the third derivative is f triple prime, but then we don't do Roman numerals after that. We do f with a 4 in parentheses. So f fourth derivative, f fifth derivative. That is what this is trying to explain over here. I don't like that they did n greater than or equal to 2. Basically, we only start doing the parentheses stuff for n greater than or equal to 4. So just change that. But this is the terminology we use. Also of note, whenever we, so this right here is equivalent to dy, or this here is equivalent to dy dx, the derivative with respect to y of a function. When it comes to the second derivative, you might see this terminology, d squared y dx squared. This means the second derivative. So just in case that comes up, let's say on a lab or something like that, or on the homework, this is the terminology for the second derivative of y with respect to x. Note, they're not actually exponents, they're just telling you to take the second derivative. Okay, so let's do an example of doing just that. This should go pretty fast. So they want to find the third and fourth derivative of f of x. So what's f prime of x? So hopefully you're flying through this without having to write it out. So look at 4x to the fifth. 5 goes to the front, we get 20, x to the fourth. What about here? 3 goes to the front, bring down the negative, we get x squared. What about here? Well, the derivative of 12x is just 12. There's your first derivative. What about our second derivative? Now we concentrate on this function. Well, here's the 4. Where does it go to the front? We get 80. Just subtract 1 from the exponent, x cubed. Bring the minus, the 2 goes to the front. 2 times 3 is 6. We subtract an exponent, get x to the 1. The derivative of 12 is 0, so nothing happens. Okay, now we're to part of the answer. What about f triple prime of x? Well, now we're here. 3 goes to the front, times 80 is 240. Subtract an exponent, get x squared. The derivative of negative 6x is just negative 6. Last part of the answer, we want f fourth derivative of x. So therefore, we look at this function, 2 goes to the front, we get 480, subtract 1 from the exponent, get 40x, the derivative of negative 6 is 0. So in our problem, our two answers are these guys right here. So these are our higher order derivatives for our function f of x equals our fifth degree polynomial. Okay, so if you recall from our first section in this chapter, you were using that limit formula to find derivatives. We were asked to find the equation of a tangent line. So the equation of the line tangent to f of x at some point. You did several problems like this, and they took forever. There was three Roman one set step 1, 2, 3, and they took forever because finding the derivative took forever. Well, guess what? That's not the case anymore. So what we're going to do is, and by the way, these problems 12 and 13 are standard requirements in calculus. So you are guaranteed to get this on your first exam and probably on your final. So be ready for it and understand what you're doing. So if we want to find the equation of the line tangent, it was a three-step process. What was the first step? The first step was find the derivative of the function. Why? Because the derivative of the function is the slope of the tangent line at any point. So what is the derivative of our function? Well, before we did that limit craziness. Now look at what we have to do. 3 goes to the front, get 3, subtract the exponent, x squared. Here, 2 goes to the front, gets negative 6, subtract exponent, gets 6x. So we're already done. I mean, that took, what, 2, 3, 5 minutes last time? We already have the derivative, and just as a reminder, this is slope of tangent at any point. Okay, so what was step 2? It was find the slope of the tangent at our point. Well, what's our point? 1, negative 2. So what is our value of x? It's 1. So we need to find f prime of 1. So what is f prime of 1? Well, we just plug it in, right? So when we plug it in, we get 3 times 1 minus 6 times 1, which is negative 3. So what is this? This is the slope of tangent, specifically at x equals 1. So we just found that the slope of this line, so note, side note, you will never get the picture on an exam, right? The picture is here for me to show you so that you can actually see what you just found. You just found that the slope of this line is negative 3, right? So it makes sense. It's falling from left to right. And if you calculated it using the graph, it would be negative 3 because this is an accurate graph. So what was our last step? It was to find the equation of this line right here. The equation. So how did we do that? Well, remember we used point slope formula. What did we need in order to use point slope formula? We needed a point and we needed the slope. So let's do that. So just to be clear, the point slope formula is y minus y1 equals x times x minus x1. If we plug in our numbers, we get y minus negative 2, which is our y, is equal to negative 3, our slope, times x minus 1, our x1. So if we just simplify this for a second, we get y plus 2 is equal to negative 3 times x plus 1. And as I told you before, you do not have to simplify that. You can leave it just like that. So this, again, our last step, is the equation of the tangent line in our picture. Okay, so you see, we went through this in about maybe a minute and a half, not even. So I'm always a bad judge of time, but whatever it was. This three-step process is super fast. It will be some of the easiest things you do this entire semester by a mile. And it should feel that way, or things might not be going well later. So this is our process. Follow it, know it well in terms of our problem. So let's do one more example to make sure you're okay. All right, so let's say we have the function f of x equals 2x minus e to the x over 2. First thing of importance. Students, for some reason, struggle with this concept. When they see x over 2, they don't quite understand that it's the same as 1/2 x. Okay, this is really important to know. And you must be able to make this designation because if I asked you for the derivative of this, students will self-destruct because they're not understanding that it is this. Because what is this? This is just a constant times f of x. What's the derivative of this? It'd just be a half. Well, students will get this, and I'll say, what's the derivative? And it's just blank. Why? Because they're not making the connection that it's that. Okay, good side note for everybody to see. So why did I do that? Because this is the same as 2x is equal to, 2x minus 1 half e to the x. Okay, that's a big deal, and you got to make sure that you're clear with that. So let's go through our process. So what's the first step? We find the derivative of our function. The derivative of our function is, well, what's the derivative of 2x? It's 2. What's the derivative of 1 half e to the x? Well, 1 half is a constant. It comes along for the ride. What's the derivative of e to the x? It's just e to the x. So the only difference between the function and its derivative is just the variable x that's sitting right here. What do we do the second step? We need to evaluate the derivative of this function at x equals 0. So we have to do f prime of 0, which is 2 minus 1 half e to the 0. What is any value to the 0? It's 1. So we're going to get 2 minus 1 half, which is 3 halves. Okay, so that is the slope of this tangent line if we draw it at x equals 0. Okay. Lastly, we want the equation of the tangent line. So if we have that, we look at our point and we go, we got our point, we got our slope, so we're going to do y minus a negative half is equal to our slope 3 halves times x minus 0. You could leave it like that, but you could also make it y plus 1 half is equal to 3 halves x. And that is the slope, or not the slope, the equation of this line right here. So that is the goal of this, beginning part of the section, is to reach the point where you can find the equation of the tangent line of some, the derivative basically of your graph, the equation of the tangent line at any point of a function. Okay, so as is probably going to be hour plus, but finally the last concept in our section on page 31 here is something that you will be using a lot in this class. I'll bring it up more when the time comes, but this is a great time to start with what we're going to do in terms of finding tangent lines. So I'm going to read here. It says, finally, it's common in calculus, its many applications, to be able to determine where on a function a tangent line could be horizontal. So look at this function right here. So I have a function drawn, upside down parabola or parabolic shape. So I can draw a lot of tangent lines here, a lot of tangent lines. Everywhere there's a point, I can draw a tangent line. But where on this, at what value of x, can I actually determine that there's a horizontal tangent line? Well, clearly, the only horizontal tangent line is going to occur up at the very top of our picture, which is drawn right here. This is the only one that's going to happen in this picture. So the question is how can we find that algebraically? It says, we know from algebra, of course, that the slope of a horizontal line is 0. Therefore, our goal is to find everywhere the slope of the tangent line of the function is equal to 0. Okay, right? What is the slope of the tangent line, folks? It is the derivative of the function. So, all we have to do in order to find where, at what values of x that we can draw a horizontal tangent is to set your derivative equal to 0 and solve. That will be the case in everything we do later, but that is the concept of importance. It is set the derivative equal to 0 and solve. So look at 14 right here. I have a polynomial that is drawn here. Again, you would not see the polynomial on exam. This is for learning purposes. So if you look at this picture, there are clearly 2 points in which we will be able to draw a horizontal tangent line. We could pick any of these other points on here, and all of them will be non-horizontal if we try to draw them. Hopefully everybody sees that. The only place where this will be horizontal is interestingly enough, at the top and the bottoms of the graphs. We'll talk about that a little bit more conceptually later, but for now, that is the case. So how do we find it? Exactly what we said. First step, find the derivative. Okay, well, look at our function here. 3 goes to the front, subtract 1 from the exponent squared. Here, 2 goes to the front, times 3 is 6, subtract 1 from the exponent. Here, well, what's the derivative of negative 45x? Negative 45. What's the derivative of 4? It's 0. So therefore, this is the derivative of our function. So what did we do last time? We ended up having to plug in a number in for x, right? So that's what we did here. We plugged a number in, or substituted a number in for x. Why did we do that? Because we knew what x was at the point. It was 0. So why is this different? Because we don't know what x is. So this is a graph. Normally you wouldn't have the graph. So we're trying to locate what value of x will be where the horizontal tangent line is drawn, which means this right here, f of x, this variable, actually, I'm not going to write it. This variable here has to stay put, which means this variable has to stay put. So where does the number go? Well, what are we looking for? We're looking for, Jesus, everything just went crazy here when I did the eraser tool. We're looking for when this actually is equal to 0. So in other words, when is the derivative 0? Well, the only way to do that is to plug in 0 for the function itself. And look at this, we have an algebra problem. So what do we do first? We note that 3, 6, and negative 45 are all divisible by 3, so let's take a GCF and get this. The 3 is of no importance to us at this point, but what are we going to do? We're basically just going to factor this function. So we're going to get x and x. What numbers multiply to get 15 that have a difference of 2? Clearly plus 5 and negative 3. So if we set this equal to 0, we're going to get x is equal to negative 5 and x is equal to 3. Okay, so look at the magic, folks. Negative 5 right here, and look at 3 right here is where the other one is created. So by setting this derivative equal to 0, we found the value of x, which produces a horizontal tangent line for our function. This is a gigantic discovery. Why? Because it's going to have to do with maximum and minimums. Note that this happens to be where a maximum is, and this happens to be where a minimum is. We will talk about that in future sections, but for now, the main concept is if we want to find where the horizontal tangent lines are, then we would obviously set the derivative equal to 0. Now note, just on a side note here, this is a completely last thing I'm going to say. So you'll notice there's a y here. If for some reason in my math lab, they ask you for the full coordinate where the tangent line is horizontal, all you have to do is take your values of negative 5 and 3 and plug them into the original function. Don't plug them into the derivative. If you plug them into the derivative, you're going to get 0 each time, because that was the whole point of this process. You take the negative 5 and the 3 and you plug them respectively, individually, into this function, and it will give you the 179 and negative 77.